Hello. In this video, I'd like to talk about a recent piece of research we carried out at the Geophysical Institute at the University of Alaska, Fairbanks, with support from NASA. This was a collaborative effort between the Geodesy Lab and the Alaska Earthquake Center. Before getting into the thick of things, I thank my collaborators for their contributions in this work. In this study, we explored new ways of using geodetic and seismic data in tandem for rapidly characterizing an earthquake soon after it occurs. The study was conducted in the context of the 2021 July 29 magnitude 8.2 Chignik earthquake that occurred along the Aleutian Plate boundary where the Pacific Plate subducts beneath the North American Plate. The earthquake was the largest event to occur in the United States in over 50 years. It was recorded by several GNSS stations, that is, Global Navigation Satellite System stations, and strong motion stations. Here, the GNSS serves as the geodetic data, and the strong motion or accelerometers serve as the seismic data. We choose this earthquake because of three factors. 1, its size. 2, its proximity to well-maintained and operational GNSS and strong motion stations at the time of the earthquake. And 3, and most importantly, due to the presence of co-located and closely located GNSS and strong motion stations. The earthquake occurred on the interface between the two subducting plates. Motion along such a fault causes the land to move, and this motion is captured by the GNSS receivers and strong motion sensors on land. These instruments can capture the velocity with which the ground moves, and we used this information in this study. The geodetic data we employ are the instantaneous GNSS velocities that are GNSS receiver velocities obtained from differenced phase observables. Meanwhile, the seismic data are integrated and downsampled strong motion or acceleration records. At the top is the 1 Hz velocity time series from the strong motion station S19K, followed by identically sampled instantaneous GNSS velocity from co-located station AC34 beneath it. At the bottom is a difference between these two time series. The panel on the right shows the corresponding spectrograms. Comparing the two co-located stations, we observed similar earthquake signals in the two time series within 0.25 Hz frequency. Using this frequency band, indicated by the orange box, we removed everything outside the identified signal to quantify the similarity. The signals were then cross-correlated to check for the extent of similarity between the two. As seen in the bottom right, the results showed a high correlation of 0.9 between the two stations. Once we checked for similarities in all co-located and closely located GNSS and strong motion stations, we identified GNSS and seismic peak ground velocities, or PGVs. PGVs are the maximum velocity with which the ground moves at a specific location. First, we use these PGVs along with corresponding magnitude scaling relationships to arrive at moment magnitude estimates for the Chignik earthquake. GNSS, strong motion, and joint datasets resulted in moment magnitudes within 0.4 magnitude units of the final value assigned to the Chignik event. These values turn out to be within the acceptable uncertainty limit for rapid magnitude estimation. Subsequently, we compared PGV contours generated using GNSS stations with those from co-located strong motion stations. As seen in the plots here, we observed similar contour patterns from co-located GNSS and seismic stations. We also tested substituting these GNSS stations in a larger network with co-located seismic stations. We found that this resulted in minor variations in PGV contours. Therefore, these results indicate that GNSS and strong motion records for a given earthquake can be interchangeably or jointly used for rapid earthquake characterization and ground motion estimation. Further details about the study and the data used can be found in our paper published in the Seismological Research Letters. Thank you.